Hello and welcome to Calsoft podcast series. My name is Umang and I will be your host for this podcast. I am associated with Calsoft as marketing specialist. Today we have with us Mr. Hirak Banerjee who will be giving us a detailed walkthrough on RAID concepts. Hirak is a senior quality assurance engineer at Calsoft. He has 4 years of experience in the IT industry with major experience in storage technology. He has brilliant knowledge of servers, architecture, functionality, hardware testing, and storage area network. In the storage domain, RAID concepts are the most important thing that are used in testing. Today, Hirak has promised us to explain in details the functionalities of important RAIDs that are widely used in the industry. Great, Hirak. It's pleasure to have you with us for today's video podcast.
Thank you, Umang. Thank you for having me here.
Should we quickly get started with this very interesting topic?
Yeah, sure.
So, can you start up with the introduction of RAID?
Yeah. So, RAID stands for Redundant Array of Independent Disks. The main motive of RAID is performance, fault tolerance, and space management or optimization. So, what does this achieve for the business? It improves the input output performance, it makes storage fault tolerant, it protects the data integrity as it provides a backup in case of a disk level corruption, helps in achieving optimal level of performance for critical systems, and that requires you to choose the right type of RAID. Now, the things that are not to be expected from RAID is that RAID is not meant for failures that occur at a data center level. In simple words, it is meant for failure that occurs at storage area network or network attached storage or on server levels, and not for bigger scale like a failure across overall data center. It cannot bridge for software level error or if there is an issue or a bug within an application. Also not in case of a user error. RAID is nowhere related to this and we won't mitigate the issues occurring at these levels. Now, there are different types of RAID that provides the basics that we need, like we discussed earlier about performance and fault tolerance. The RAID types start from RAID 0 to RAID 50 and RAID 60, but today we will cover the ones that are widely used in the market. And those are namely RAID 0, RAID 1, RAID 5, RAID 6, RAID 01, RAID 10, RAID 50, and RAID 60. So we'll be starting with the first one, that is RAID 0. RAID 0 evenly stripes data across multiple disks. It operates at a block level and it allows to create large volumes. But it cannot tolerate failure. RAID 0 has zero window for fault tolerance. This is because it has no mirroring or parity features. I will cover in brief how mirroring and parity works in case of other RAIDs. This RAID level, RAID 0, is a big no-no for production setups. This RAID 0 is advisable to be used only for user-based self-learning servers, has downtime in case of a failure. Now, downtime criteria are a big no for production level servers as it can hamper business. The minimum number of disks that can be used is 1. When more than one disk is used, the data gets saved as blocks as seen in this picture here. And the data blocks on each side are unidentical. A1 goes into disk 1 and A2 goes into disk 2, and the process continues as an alternative zigzagged path as shown in the picture. This gives optimal performance as the load isn't shared between the multiple disks. Moving on to the next topic, that's RAID 1. It is used for mirroring the data between the two disks. It also operates at a block level. It can tolerate a failure of one disk as the data has been mirrored on the other disk. In simple words, the data has been replicated and stored in the other disk. So if one disk fails, the other disk has the data safe in it. As we had seen the data paths getting stored alternatively in case of RAID 0, here in RAID 1, the same data gets stored on both the disks, just like a pairing set. RAID 1 can have half the volume as compared to RAID 0 as the data is getting stored in the paired disk. For RAID 0, that wasn't the case, as you can keep adding disks which will increase the volume since similar data is not occupying multiple number of disks. Now, before moving on to the next, that is RAID 5, I will briefly cover RAID 4 as there is a concept of parity that is used in RAIDs starting from RAID 2 till RAID 6.0. I will take RAID 4's case as an example because RAID 2 is not very popular and RAID 3 is somewhat similar to RAID 4.
So, Hirak, before moving to other RAIDs, can you explain what is parity?
Yeah, so in simple words, parity drive is used in RAIDs to provide better fault tolerance as it uses XOR function in recovering the lost data. Well, in bookish language, the XOR function is known to be as either one or the other, but not both. So by that logic in RAIDs, if XOR function of all the data in the RAID array is put on a parity drive, and if any portion of the data among those drives is lost, then by the remaining data in the other drives, we will be able to recover the lost data. We will see how that works in RAIDs, taking the example of RAID 4. As you see this image of RAID 4 setup, the data are striped across the drives and there is a dedicated drive for the parity. Just an FYI, RAID 4 requires at least 3 disks to operate plus the parity disk. So in this case, the parity bits are horizontally generated from its corresponding data bits. Well, as in to understand, A1, A2 and A3 is used to generate parity bit AP, and likewise B1, B2 and B3 is used to generate parity bit BP, and so on. So if from the first horizontal slot a given data bit is lost, let's say A2, then using the XOR function of the parity bit, we will be able to recover the lost bit, that is A2. Now moving on to RAID 5. Here too the concept is same to some extent like in RAID 4 which we previously discussed. The data is striped across the multiple disks, but the difference lies at the arrangement of the data and parity bits as seen in the image. The redundancy has been built based on distributed parity structure. As you all can see, the parity bits are placed in between the horizontal array of the data bits, unlike as in case of RAID 4. It works pretty much the same as RAID 4, but it doesn't require a dedicated disk for keeping the parity bits. RAID 5 provides very good redundancy, that is fault tolerance basically, and better performance, and it provides more disk space. A minimum of 3 disks are required for RAID 5. Moving on to RAID 6. RAID 6 has a similarity to RAID 5 as it stripes data and parity across its multiple disks. The primary difference that makes RAID 6 stand out is that it uses double parity. As we can see in this picture, there are double parity bits in each horizontal and bit lines, each horizontal bit lines. The interesting part here in RAID 6 is that it incorporates horizontal and diagonal parity. Let's understand how that works. Well, looking at this picture, data bits A1, A2, A3 will be used to create the parity bit AP, and A1, B2, CQ and D2 will be used to generate parity bit AQ. This particular thing gives RAID 6 an added advantage of fault tolerance of up to 2 disk failures. So if 2 disks fail within RAID 6, we will still be able to recover our data. RAID 6 requires a minimum of 4 disks to be operational. Now, before moving on to RAID 01, now let's take a look at nested RAID. Nested RAIDs are a combination of 2 RAIDs which gives the combined advantage of performance and tolerability. That includes RAID 01, RAID 10, RAID 50 and RAID 60. Note that in these combinations, as we speak, RAID 01 or 10, the first notation implies to the RAID that will be inside the loop, and the second notation implies to the RAID that on top of the one that's inside. I mean, just in a cruder form, in RAID XY, X and Y are the 2 RAIDs that are being combined, in which RAID X will reside within RAID Y. You will get a clearer picture when we discuss the nested RAID types. So the first one we are covering in nested RAID is RAID 01. So as seen in this picture, the data are striped blocks within a mirrored structure of disks. Here RAID 0 is nested inside RAID 1. The data in the disks are striped as they have been applied as in RAID 0, and that RAID 0 structure has been mirrored as a whole, creating a parent RAID 1. So RAID 1 is configured on the storage controller in this scenario. The storage controller will send the same set of data to both the RAID 0 structures, and accordingly RAID 0 will stripe the data. This is known as mirrored striping. Moving on to the next one, we have RAID 10 or RAID 1 plus 0. This is the exact opposite of the nesting that was done in case of RAID 01. Here RAID 1 is nested within RAID 0. In this scenario, the blocks of data are mirrored in a striped structure. Here the storage controller level RAID 0 is configured as RAID 0 is the parent in RAID 10 structure, which indicates that the data which the controller sends will be striped across the 2 pair of RAID 1s. As striping, we know, is putting up the data blocks alternatively among the 2 disks in RAID 10 structure. The data blocks A1 goes into the first RAID structure and it eventually gets mirrored. The data blocks A2 goes to the second RAID 1 structure and that too gets mirrored within the RAID 1 structure. A minimum of 4 disks are required for RAID 10. The next up we have is RAID 50, which means RAID 5 will be nested in RAID 0. RAID 5, which we have already discussed, uses distributed parity, will have the same functionality here as well. The parent RAID is that RAID 0 will stripe the data received from the storage controller to the 3 sets of RAID 5s. To set up a RAID 50, multiple sets of 3 disks are required. The minimum number of disks required will be 6, that is 3 for each set of RAID 50s. It's very good as it provides good fault tolerance and space and also good performance. So now moving on to the next one, we have RAID 60. In RAID 60, nested sets of RAID 6 within a striped structure of parent RAID 0. This is the best of RAID 6 combined with striping, which is widely preferred. RAID 6, as we know, uses double distributed parity and horizontal diagonal parity data recovery structure. And all of that striped across multiple sets gives a very robust nested RAID. Sets of 4 disks are required for each RAID 6, and that multiplies to the desired number of RAID 6s to be used. The minimum requirement would be 8 disks, that is a minimum of 2 RAID 6s having 4 disks each. Now, reiterating my previous note about RAIDs, the RAID concepts can be applied on servers, storage area networks, and network attached storage. That's all I have from my end.
Thanks, Hirak. It was a great session. For our audience, I would like to quickly sum up. We have discussed RAID concepts and their importance in details. We will now take your leave and promise to bring many such insightful technology sessions in near future. For any queries, please write to us at marketing@calsoftinc.com and stay tuned for our future video podcasts.